In this last unit of the course, we're going to discuss the dynamics of systems in greater than 2 dimensions, namely more than 2 dynamical variables. As we'll see, systems of more than 2 variables are wondrously complex and beautiful in their dynamical behaviors, but there's a price to pay in that they're also much more complicated. So we'll only give a very brief glimpse into these greater than 2-dimensional systems by studying a number of paradigmatic examples. But let's begin by contrasting the fundamental difference between flows in 2 dimensions and flows in greater than 2 dimensions. So the point is that in 2D, trajectories are highly constrained by the Poincaré-Bendixson theorem. That is, that if we have a 2-dimensional flow as a function of x and y, and somewhere in this space there is a closed curve in which the flow is inward everywhere along the closed curve. What that means is that the flow has to stay inside of this closed curve. No way out is another way of putting it. So this feature basically constrains the nature of the flows because the flow goes inward and it has to stay inside. There's no way out. However, if we're dealing with the flow in 3 dimensions, if we find such a curve where the flow is inward, the flow can escape in the 3rd dimension. And this gives rise to very different types of dynamical behaviors in greater than 2 dimensions than in 2D. So in greater than 2D, let me just list some of the basic features of trajectories that do not happen in 2 dimensions. First point is that trajectories can be irregular. So we've seen that in 2 dimensions, flows are smooth, and we can think of the flow as some kind of like 2-dimensional compressible fluid in which you end up at fixed points or limit cycles. But in 2 dimensions, much more rich behavior can occur, and the flows can in fact be irregular. Another important feature is that there's sensitive dependence on initial conditions, something that does not happen in 2-dimensional flows. And this feature of sensitive dependence on initial conditions is often what's known as chaotic behavior. And finally, in 2 dimensions, we saw that flows could converge to limit cycles, to fixed points, they could go off to infinity. But in 3 dimensions, flows can converge not to just a fixed point, but to strange attractors, namely fractal sets in 3 dimensions. And so the flow is extremely hard to characterize because of this feature that it doesn't look like anything regular, and it takes a lot of effort to try and ferret out this feature of strange attractors. All of these features, irregularity of the orbits, chaotic behavior, strange attractors, there's no general analytical methods to uncover when this occurs. So instead of trying to be systematic about this, I want to present 3 paradigmatic examples that begin to illustrate and give a glimpse into the beauty and wondrous features of 3-dimensional dynamical systems. So the 3 examples that I'm going to present are 3-species competition. I'm going to present the periodically driven and damped pendulum, and finally the Lorentz model, an idealized model for large-scale flows in the atmosphere. Hopefully, by looking at these examples, we begin to get a little bit of insight into the wondrous behaviors of 3-dimensional dynamical systems.